Hello guys, nice to see you. Good afternoon. Hello everyone. So, uh, last time good afternoon. Last time we introduced concept of temperature and the way how we can measure temperature. Also, our topic of discussion was the thermal expansion of solids, like linear and volumetric thermal expansion. So we managed to find a relationship between the linear and volumetric thermal expansion coefficients. And today we proceed further. First, we will discuss one special case with water specifically. And afterwards, I mean, in terms of thermal expansion. And afterwards, we will start discussing ideal gas as some other form of state of matter, which does not follow the same principles as solids in terms of response to temperature, for instance, and because of its intrinsic, inherent properties, which we will discuss, and then we'll consider empirically derived equations which describe behavior of ideal gas under different conditions. Okay, let me change the camera to our slides. And talking about thermal expansion, it would be necessary to mention about water, because so far we claim that objects expand with increase of temperature, which is a valid statement for most cases. However, water behaves in a more complex way. So if we consider density of water versus temperature, this dependence will be something like this. So let's say if we let's consider some temperature 4 degrees Celsius, then if we go to higher temperature, water experience thermal expansion, means that the density of water decreases. So that will look like this. That's normal behavior, which we would expect. However, at 4 degrees Celsius, it reaches maximum density. Yeah, sure, you can ask. I have a question about midterm. Oh, you can unmute yourself, so you can ask your question. Okay, you can ask later. But sure, midterm is coming. So I believe soon we will send you some notification. So it will cover topics until thermodynamics and molecular physics. So the last topics from mechanics, which haven't been covered previously during first and second midterm. So it will be the same process as you are familiar already. We are long kappa, we'll have 45 minutes. It will be 6 problems. And yeah, there will be 1 hour to some time window and 15 minutes, 45 minutes for actual work on your midterm. So nothing new, no changes to this procedure are planned. Okay.
Can I ask a question about the exercise on 1 kappa?
Sure, yeah.
There is an exercise called vibrating platform, where the amplitude of the oscillation is given, and the vibration platform is oscillating at a controlled variable frequency. And we have to find, and the small rock of unknown mass is placed on the platform. At what frequency will the rock just begin to leave the surface so that it starts to clatter?
Yeah, okay.
So here, how to find the frequency?
I mean, that's a question to you guys. Need to think about it. So we definitely don't solve problems here from like homework. You have this recitation for that. But I believe if you think a bit about this problem, there should be a clear answer to this question. Sure, and on the recitation, all these problems which you have for homework assignments, best to my knowledge, they are solved on recitations, and even moreover, they are available on YouTube. So there was another question about constants. Will constants be shown under every question in midterm? Those which are necessary, they will be shown. If they're not shown, means that they are so common that you will not have much options to use the wrong value for this constant. But those which are more specific, for sure, they will be given.
I asked this question because I had problems with it in the textbook while solving the problems. So there are a few decimal changes in the constants. Then the answer was wrong because of that.
Oh, can you repeat, please? But unfortunately, the sound quality is low.
I'm asking this question because I had this problem while doing the problems in the textbook, and there were some differences in decimal points and the constants, and the answer was wrong because of that. That's why I'm asking that question.
Okay. Yeah, I understand your concerns, but again, those constants which are not commonly used, they will be given, so you will have exact number. But something like G, for instance, which is 9.81, that you should be already familiar with this constant, and it will not be additionally specified in the text of the problems. But something like, for instance, if you need to solve a problem related to gravity, and there will be a radius of Earth and mass of Earth, then these numbers will be given, because it may be that different sources provide a bit different values. So these values will be given and mentioned explicitly in the text of the problem. However, if we have some fundamental constants, they should be specified with quite high accuracy, and unlikely that it will be the main reason for the deviation of your answer from the correct by more than 1% because of using different value for the established constant. There could be some other reasons on top. Okay, let us continue. So at 4 degrees Celsius, the density of water reaches its maximum and then starts to decrease while we reduce temperature from 4 degrees Celsius to 0 degrees Celsius. So such an unusual behavior means we kind of reduce temperature instead of shrinking. This water, while it's still in liquid phase, start to expand. And we get maximum density 1.0 grams per cubic centimeter explicitly at 4 degrees Celsius. So the change in density is not so dramatic, of course, within narrow temperature range, but that is enough to define interesting behavior. So in the temperature range, let's say from 4 to 7 degrees Celsius, density of water increases as temperature decreases. So that means that the cold water from the surface, let's say the temperature of air drops and the surface of water cools down. So this pre-surface area of water cools down, becomes denser, and by convection, just because it's heavier, it goes down on the bottom of this reservoir. So that is kind of expected behavior. However, that will happen only until temperature reaches 4 degrees Celsius. In the temperature range from 0 to 4 degrees Celsius, there will be different behavior. Water, which is pre-surface water, still continues to cool down. However, in this case, the density decreases because of thermal expansion. That means that cold water doesn't sink anymore to the bottom of the reservoir, but stays on top because it's lighter than a little bit warmer water underneath. And it cools down until 0 degrees Celsius and forms the ice layer on top. So while cooling down continues, water layers under ice will also cool down and also stay next to the ice because they will be lighter than water underneath. So ice thickness will increase. And that's why we observe formation of ice on the surface of water reservoirs, not in the bottom. And that's why at some point the thickness of ice becomes so large that it works as an efficient thermal insulator from very cold external temperatures, and the bottom part of water reservoirs remains liquid, which is the key requirement for surviving for all organisms which live in this water, because otherwise, if it's frozen from the bottom to top, and then it would be frozen completely, and no options for life to survive. And that's one of the key feature which allow to evolve more complex organisms in oceans and some smaller volumes of water, which allowed the evolution of life on our planet. So this unique feature of water in terms of changing the trend in thermal extension within 4 degrees Celsius played one of the key role in the development of life on our planet. And I believe that that's reasonable feature of unique feature of water, which should be known and considered. So now we had a chance to discuss a little bit thermal expansion of solids and also water. And we remember, for instance, if we have some volumetric change in some volumetric thermal expansion, we can write that delta V is equal to beta times initial volume times delta T. So that equation is quite useful if we know beta means volumetric thermal expansion coefficient. We can calculate change of the volume because of change of temperature delta T. However, for that reason, for that purpose, we need to know initial volume of the material. So that applies to solids and liquids because they always occupy certain volume, which is defined by the quantity of the material. However, we cannot apply this equation to gases. Why it happens? In the case of gases, the interatomic forces between atoms or molecules of these gases are very weak. And at some point, when pressure is quite low, can be completely neglected. Means that gas occupies always all volume which is provided for it, regardless of its quantity. So in this case, there is no possibility to define the initial volume. So in order to deal with gases, we need to develop some mathematical, like some analytical equations, which will describe its behavior at different conditions, means at different pressure, volume, and temperature, because all of these parameters will be interconnected. So today we will consider ideal gas, and definition of an ideal gas. The key definition is when atoms of the gas are considered to interact with each other only in via collisions. So it means they will collide with each other, and that's the moment of interaction, and there will be no other interatomic interactions because they are so weak that we can cancel them out. And atoms are considered as mathematical points. So we don't consider any shape of the atoms because we neglect with their size in comparison to the volume ideal gas occupied. And they are so small that the volume of the individual atoms, or even all atoms which are in this volume, are negligibly small in comparison to the volume the gas occupies. So it is convenient to express the amount of gas in given volume in terms of the number of moles. So usually denotes number of moles, and that is equal to mass of gas divided by molar mass of the substance of the atoms which form this gas. So you can determine molar gas from the atomic mass of each element, and it is measured in grams per mole. So 1 mole of any material consists of Avogadro's number of atoms. So Avogadro's number, Na, is equal to 6.022 times 10 to 23. And it tells us, it provides the number of atoms or molecules in 1 mole of the substance, of the material. So keeping this in mind, we need to consider several possible processes and conditions under which parameters of ideal gas can change. So let us start with isothermal process. Means that the process of during this process, temperature of the ideal gas doesn't change. So we can consider some model system with ideal gas in like some cylinder with a mobile piston which can move, and here we have our ideal gas. So now let us consider different processes which can happen with this gas. So first option, as I mentioned, is isothermal. That means temperature remains constant. In this case, based on experimental investigations, so it's all results obtained experimentally, we can write that pressure of this ideal gas, like inside this volume, changes reversely, like, okay, it's proportional to 1 over volume. So we can write that pressure inside the ideal gas under constant temperature, so isothermal process, is proportional to 1 over volume. And in other words, we can write that the product of pressure and volume of the gas is constant. So that means if we go from one state to another, when we had P1 times V1, that should be equal to P2 times V2. So we go from one state to another. One state is described by pressure and volume, V1, P1 and V1. Then we are in the other state, and that state should provide us different values for pressure and volume. However, the product of these two parameters should remain constant and doesn't change if temperature remains constant. So that is isothermal process. Another important case for like scenario for the processes in ideal gas is so-called isobaric process. Isobaric process means that we have pressure constant. So in this case, obviously, volume and temperature are changing. So under constant pressure, it is shown experimentally that volume is proportional to temperature. In other words, we can write that the ratio between volume and temperature remains constant if pressure is constant. So again, if we consider two states, which are obviously described by different values for volume and temperature, we can write that V1 over T1 should be equal to V2 over T2. Of course, only if pressure remains constant. Another important parameter, like process to be considered, is isophoric, or sometimes it's called isovolumetric. So isophoric. And obviously, for this case, we have constant volume. So under constant volume, there are two parameters which are changing, which is pressure and temperature. Pressure is proportional to temperature, and the ratio pressure divided by temperature remains constant. So we have P1 divided by T1 is equal to P2 divided by T2. So we considered now three most common and important processes in ideal gas. And summarizing this, we can write so-called the equation of state of an ideal gas, which already takes into account all these three experimentally observed cases. So the, the equation of state for an ideal gas looks as follows. We have product of pressure and volume equal to N times R times T. So N stands for number of mole, and we can write mass of the gas, which is comprised in volume V, divided by molecular weight of this substance, and times R T, where R is some constant, which is called universal gas constant, and we will. It's possible to show experimentally that in case when we deal with low pressure, so let's say it approaches to 0, when the loss of ideal gas can be extrapolated on real gases. So we obviously need to deal with gases under low pressure. In that case, we can neglect with the interaction between atoms of this gas besides their direct collision. So in that case, the ratio P times volume divided by number of moles and times temperature is equal to this universal gas constant R. So assuming that we operate with pressure, we measure pressure in pascals. So 1 Pascal is equal to 1 Newton per square meter. We get the value for this universal gas constant, which is R equal to 8.314 joule divided by mole Kelvin. So that is the value for this universal gas constant, which is included into the equation of the state of an ideal gas. So that's very important equation. So you definitely need to remember it, and also values for universal gas constant should also keep in mind. So now, in terms of physical meaning of this universal gas constant, there's another thing what will help you to understand its meaning, and also will probably help you to remember this constant. So the physical meaning of this constant, or its value, is the work done by 1 mole of gas by expanding under heating by 1 Kelvin. So value of universal gas constant, its physical meaning, is the work done by 1 mole of gas, of ideal gas, obviously, expanding under heating by 1 Kelvin at constant pressure. So that is the condition when we can provide physical meaning of this value of the gas constant. Also, another parameter which could be useful to remember is the volume. It's also kind of constant value. The volume of 1 mole of ideal gas under standard conditions. So if we consider N equals unity, means we deal with 1 mole of an ideal gas, then V naught, this volume occupied by 1 mole, will be given by equation R times T divided by P, universal constant times temperature divided by pressure. If we assume so-called normal conditions, and that is 0 degrees Celsius or 273 Kelvin, and pressure equals to 1 atmosphere. So do you remember how many Pascal are in 1 atmosphere?
$10,000.
10,000? No, 100,000. Yeah, something like that. You are right. So something like 101,000 Pascal. Sometimes temperature is measured in bars. So 1 bar is 1 atmosphere. And since it's quite high pressure already, pressure can be measured in millibar. So it 1,000th part of 1 atmosphere. But most common way to measure pressure is in Pascal for general physics purposes. But in industrial applications, usually you will see millibars. So under these conditions, this value for the volume occupied by a single mole of an ideal gas will be equal to 22.4 liters. So that is another constant related to ideal gas, could be useful in some cases. But of course, you need to remember that this volume is defined at very specific conditions, which are given here. Because obviously, if you change these conditions, the volume will be different. So another thing what is good to mention here, that this ideal gas state equation is often also expressed in terms of total number of particles which this ideal gas consists of. So in that case, we can write that pressure times volume, again, it's equal to number of moles times universal gas constant times temperature. And we can write that this in other terms is equal to capital N times universal gas constant times temperature divided by Avogadro's number. So, so this ratio N to NA gives us the number in how many times more atoms we have in our volume than Avogadro's number. Means, in other words, how many moles we have in our volume. So in that case, we can rewrite this equation in another form, which are quite widely used. And you should also definitely keep this in mind. So then we have total number of atoms which form the ideal gas times Kb times T. This Kb is also a constant, it's so-called Boltzmann constant, and that is equal to universal gas constant divided by Avogadro's number. And it is equal to 1.38 10 to minus 23 joule per Kelvin. That is Avogadro's constant, Boltzmann constant. You need to remember its value. You need to also remember the form of the equation of the state of ideal gas in terms of total number of atoms, not only in terms of number of moles. So with this, we can sum up our discussion. So we first considered some unique features of thermal expansion of water, which are remarkable, and we kind of usually don't think about it, why ice is on top of water, not on the bottom. That actually explains this reason. Also, the main part of our discussion was introduction of an ideal gas, which defined as a system of mathematical points which are considered to be atoms, which don't interact with each other besides direct collisions. So this model is indeed applicable to real life gases. However, they should be at very low pressure. At extremely high pressures, we cannot apply these rules for ideal gas to describe behavior of real gases. Then we considered three most important processes: isothermal, isobaric, and isophoric. It described how, based on experimental results, there was shown how different parameters, pressure, volume, and temperature, depend on each other. Based on all these three processes, it is possible to derive already, like not derive, but summarize these three cases together and get the state equation of the state of an ideal gas. We also introduced a new constant, which is like two new constants. First is ideal universal gas constant, R, and also Boltzmann constant. It's when you want to write this equation for the state of the ideal gas in terms of total number of atoms, which are comprised in the given volume. Then we operate with Boltzmann constant, which is defined as the ratio of universal gas constant and Avogadro's number. So we mention here very key properties of ideal gas and its features under different conditions. Main summary is this equation for the state of ideal gas. Please keep this in mind, don't forget, because that is the fundamental of equation necessary for solving many problems in molecular physics related to properties of ideal gas. Okay, I hope this was clear, everything. If you have any questions, you're welcome. Not, you can maybe ask some questions later if you have on these ideal gas properties. We will proceed further with our discussions on Friday. So take care, have a good day, and see you all guys on Friday.
Thank you, goodbye.
Thank you.
Bye-bye.